Last time I mentioned a particle in a 2D box, and it's unbelievably simple. The Hamiltonian is just, you simply add a part for y, and I guess if it's three-dimensional, you can add a part for z as well. The wave functions are just multiples, psi x, psi y. Again, I did link. I was a little bit late. I linked them this morning, so they're linked on the website. Remember, look at YouTube if you are hankering to catch up, because I'm kind of bad. I'll post them to YouTube and I'll forget for a day or two to link it to the website. Anyway, so it's on the YouTube channel. So there really isn't much to this, and that's why I really didn't want to blow a whole lecture on this. I mean, this is really it. The part that's also interesting is that you end up with degeneracies in the quantum numbers. You can have nodes. Nodes are what give you high kinetic energies, and you can now have nodes in two different directions. That leads to a degeneracy. If you have a node in X, that energy of that wave function is the same as if you had a node in Y, and that assumes, of course, that the lengths of the box are the same in X and Y, which, of course, I would always make it that way because it's just complicated enough. Anyway, so just watch the extra lecture, first 10 minutes on that, and again, it's multidimensional in X, Y, and Z is so easy that it's not worth devoting a whole class to. It's absurdly simple. Now, where we were on, okay, this is kind of cool. I want to point out something that's kind of neat about, we were doing vibration, and our first foray into a potential energy that's not flat or not there. And flat is almost the same thing as not there. Remember, we're doing flat potential surfaces, the homework you're doing now. It's all about identifying a boundary condition. Well, the wave function has to be 0 at 0, something like that. The wave function has to be smooth and continuous, something like that. It always comes down to that. So they're not terribly difficult. What we have to do here, now that we're into more advanced stuff, is now I've added a harmonic potential, which means that I'm describing a chemical bond at this point. And maybe don't write this down, but what you've got is you've got the kinetic energy of the wave function, and this is always the hard part. This is the double derivative. And so what you've got to have, when you do the double derivative, right, it's some constant. Who cares about constants? You're doing the double derivative of the wave function. What it's got to do is return the energy times the wave function. Now, this is what you're used to, but what I'm saying now is that it's got to also eliminate the potential energy, because the potential energy now has an X in it. Right, now that's what this is where it gets like way more difficult. So you've got much more complicated wave functions because the double derivative still has to return itself, but now it's also got to basically like account for, or more mathematically eliminate, the potential energy term as well. So and so here's an example. You may have noticed that I've actually had you do these eigenvalue equations. I've had you do a double derivative of a function plus x squared, and then I threw at you e to the minus x squared as a potential eigenfunction. You actually did that on homework 3 or something. So you've actually already seen this before. So anyway, here's the Hamiltonian. Now, I also mentioned that what we're doing from now on is no longer, well, I mean, I know that I have a textbook that shows how you do the second order differential equation. What the heck? How you do the second order differential equation solving to get to the wave functions. And the wave functions, you have energies, and I'll get to that today. It's 5 pages. It's definitely, you folks that know enough math to do this, it's just 5 pages long. It's really dense. It takes more than one class period. So what I tend to do is, I tend to just write the Hamiltonian, and I'm doing this from now on. I'm just going to write the Hamiltonian, not worry about spending days on algebra with some calculus and some algebra with some calculus. Instead, I just show you the answers. Then what I'll do is, and I'm doing this today, I'm going to plug those answers back into the Schrodinger equation and show that they work, and I show that they work by getting the energies. There's some other properties you can get as well. I'm going to show one example today. Once we have these wave functions, and these are wave functions of the Hamiltonian, so we think of them as real, we can then do other things with them, query other properties. And none of these models are ever the same, so I'm going to do something really unusual with this one today. Anyway, that's what I'm saving that. Okay, so anyway, the wave functions I had, okay, we have the normalization constants. Here's the ground state. Remember that these are characterized by a quantum number, which is, we call this yi. And this comes about by, Chinese, I'll save that anyway. So the quantum number, which is basically the number of nodes, when you do the bloody second order differential equations, that there's a quantum, that there is some kind of index that gives you multiple answers. It always just kind of pops up. Again, if we were calc experts, we were math majors, that would totally make sense. And anyway, it actually makes sense chemically, right? So we have a ground state, first excited state, second excited state. So when you do the second order differential equation solving, you have a solution, but you find an infinite number, and they're always characterizable by some kind of index that oddly happens to be a whole number. It often goes 1, 2, 3, 4, but in the case of vibration, weirdly starts at 0, and I think that's just how it comes out of the math, the second order differential equation solving. I don't really, I wish I understood that a little bit better, but anyway. So the quantum number 0 is the ground state in this case. Vibration's weird. Remember when we did particle in a box, we had a quantum number, which was the number of nodes, and it started with 1, 2, 3, 4. 1 actually corresponded to no nodes. That's actually really common. When you solve quantum things, you always have a quantum number. It always starts with 1 except for vibration. Go figure. Again, every one of these is different. No idea why. So anyway, so 0 means ground state. We have a normalization constant. I'm not worried about that. Then we have a bell curve, and I've drawn that here. The next excited states are generated by those Hermite polynomials. I'm just talking about what I talked about on Friday. In the first excited state, it's just basically an x, whatever, and that makes an even function odd. We also covered the fact that we did this for the first excited state. It's obvious from the ground state the expectation value is 0. Don't forget that also means that, remember that the x-axis is actually the displacement from equilibrium. The x-axis is the displacement of the bond from equilibrium. And we talked about that at the very beginning of the lecture on Friday. So the fact that on average the ground state is centered at 0 means on average the bond is at its, CH bonds are 1 angstrom. So on average the CH bond is 1 angstrom. I mean, there you go, it answers itself. But what we also, so that's a no-brainer. You can just look at it how I drew it. But I'm also kind of fascinated. We actually saw this with particle in the box too. The harmonic potential and particle in the box wave functions, they actually really almost look the same, with one big difference that we're covering today. But anyway, the first excited state has a node at 0, yet the average position is still at 0. And so we covered that last time. In fact, I believe all of the vibrational wave functions, harmonic wave functions, are on average not displaced from the equilibrium, so that makes sense. Anyway, it's just a question that can be asked. So what I was going to do today, and this is going to be kind of awful, I want to do energy, and then I told you that there's this like one, the thing about quantum is it gives you energies, and those you can relate to your spectroscopic observables. That's because your spectroscopic observables are like ground to first excited state. That absorbs radiation. Whatever that energy is, turn that into frequency, and then you look at that frequency of light. Anyway, it's freshman chemistry stuff, right? So fine, and that does an incredibly good job, which is awesome. But quantum also predicts unusual things if you know to look. So we're covering that too. Okay, when it comes to energies, I like to do it this way. I don't like to do this expectation value way because ultimately the expectation value is for when you have a problem with the eigenvalue equation not working. So remember, we pretty much always tell you to do things in the expectation value way, to do it this way, right? The problem is it's more complicated, but then it just spits out a number. It would just spit out the energy. Okay, that's fine, but it's more complicated. It also works, though, remember, when you have a problem with the eigenvalue equation not working, then this one will. So that's kind of awesome. In this case, we're going to do the ground state. When I put this into here, it's not terrible, but I don't want to do that and then throw in another wave function and then integrate it. I don't want to do that. It's just, no, I'm not going to do that, okay? So I'm going to do it this way. And then we're going to do an application, an unusual prediction, which is true, which is really, I think you'll like that part. This is kind of boring to be blunt. And then we get into rotation, so I think I'm going to get into that today. Anyway, so I'm actually still reviewing, oddly enough. Did any of you have any questions at this point? We're okay about this stuff. And the only thing I can remind you is, since I'm not turning this into differential equation class, just don't get bogged down with the constants. These, like last time we did average value, and it looked nasty, but it's really just a bunch of constants. Once I had set up the expectation value in x, it first looked bad, but then I just put all the constants together. It didn't look bad at all, and then you can, of course, look at calculate identity, and then you're set. So, and we're going to be, this is basically the rest of the class.
The ends of the constant in front, are those, do you get those from boundary conditions?
Well, I mean, everything ultimately comes from some kind of boundary condition once we're outside of the freeway. No, I do have, remember I showed some formulas for these wave functions for the Hermite polynomials. That's where you get the excited states.
Yep, I remember the
I have a formula for the normalization constants as well. I just didn't show it. Yeah, I didn't really need it. I actually do in this case, so I will show you the normalization constant for the second part. But yeah, for the most part, see that's the thing I like about, I prefer eigenvalue ways of solving things. It's because the normalization never matters. It just decomplicates it. So anyway, I'll show you that. So I like doing eigenvalue equation ways of solving things because I can always ignore the normalization. If you're doing expectation value way, the normalization is the most critical part, so you can never forget it. Well, here, let me just do it, and you'll see that pop right out. And I'm going to call the normalization constant n, and it's not very. It's like 1 over the square root of pi alpha. It's something very simple, right? It's nothing to even worry about, but I'd rather not deal with it, and I can do that when I do this with expectation, with the eigenvalue way. So anyway, this guy is always here, it's always here, annoyingly so. Double derivative, and like I say, I may forget the little 0 there, not that it matters. And I'm just going to do the ground state. And remember, I told you to be very careful about alphas, looking like 2s, especially in my hands. Okay, now recall that all of the difficulty is right here. All the difficulty is right here. When we do potential energy, because potential energy is almost always a static, it's just x, or x squared. You don't do anything with that. It's just stuck. You're stuck with it. Don't ignore it. Remember that I had to do a problem where, an eigenvalue problem, getting you used to eigenvalues, and every one of you had problems with it, simply forgot that there was multiple terms. Okay, now this is all we need to do. This is the left half. I don't need to do the right half because this is the left half turns into the right half, right? Equals to e side. This is going to turn into that. So I just actually need to just work with this. And then I already got rid of it here. Not that that matters. Again, that's why I like this. All right. Okay, so, and I can actually just ignore this. I can ignore this because, I have to ignore this. There's nothing I can do with it. Okay, double derivative. The first thing I like to do is, if you've seen this a zillion times now, decomplicate, get rid of the constants. There we go. Tell you what, let me do the first derivative. I'm not going to do 2 derivatives in my head. Maybe I could, but I'd be tempted not to. Okay, so first derivative. Okay, I don't have a product rule, so nice. What have I got? I got a minus x squared over 2 alpha squared. Let me double check. Yeah. No. Okay, exponentials, hold on, start easy. Exponentials always survive derivatives and integrals. Usually when I belt that out, I can get my head together and then I'm kind of fine. Exponentials always survive derivatives and and integrals, but then I have the derivative of the argument. Okay, so I have a 2x. Right, there we go. Right, okay. Right, so when I get, you saw me just mess that up. And so what I do is when I realize I'm messing up, I just write the exponential because I know that that's always there. And again, that's just my own mental saving move there. Plus 1/2, yada, yada, yada. Notice that this actually simplifies quite a bit. Here, let me just do the next step. And again, I can just, all I'm going to do is I'm going to find my wave function and just multiply the normalization constant. And of course, in the eigenvalue way, then I don't need to worry about it anymore. Okay, so now I'm doing a derivative, and now I say I have a product rule. I've run into a product rule, but I know I need to. Remember that the way I described how kinetic energy has to return the energy minus, and it has to return minus the potential energy. So I know that I'm always looking for a product rule. I know that when I do kinetic energy, I've got to run into a product rule because that allows the answer to bifurcate. One gives me the energy, the other one will wipe out potential energy. So look for that. When I throw these at you, look for that. Okay, so I've got a product rule. So one of them is going to return the wave function times the eigenvalue. And I know that will be when I take the derivative of x first, because then it's gone, right? So let's do that. Here, so I've got, okay, 1 over alpha, I just got 1 over alpha squared, right? I've got minus, I've got x over alpha squared, but I'm doing the derivative of x. So there's really nothing to this. And I know that this has to be my answer. That has to be my answer right there, because I see the wave function. So look at that, I've got my normalization constant, e to the minus x squared. Look at that, the answer is even positive, which I'm thinking that the energy should be positive. That's not always true, but the answer is positive. I've got h bar squared over 2m alpha squared, so I can already tell that that's my eigenvalue. Okay, but now I got to make sure that this works. So now I've got to do what? Now I've got to leave this part alone, then do the derivative of the other thing, but I already know how to do that. That's minus 2x over 2 alpha squared. The exponential always survives. And now I'm going to write the 1/2 kf. Now remember that kf, that is the spring constant, and I can turn that into a function of m and alpha and yada yada yada. Okay, so again, remember I was lazy and didn't put that there. Okay, now, you see, I know it looks kind of hideous. Jeez, it is hideous, isn't it? Oh, I'm sorry. Anyway, all right, so, hold on, now I got to take it aside. So you need a whole piece, hopefully you start with a whole piece of paper. I should have mentioned that to you. Okay, so I'm looking here now. Oh, look at that. X squared, I got an x squared. Oh, except it's positive, right? Okay, hold on. This is positive, but this is positive. And I can see that this should wipe it out, but it's positive, right?
Distribute the negative.
Right here, right, so it's negative. So you see I've got a minus x squared plus x squared. The only thing I've got to do is I've got to have 1 over alpha to the 4 better be 1/2 kf. Okay, so let's figure that out. Now, you see, question? You see how, so this is x squared e to the n, e to the wave function, 1 over alpha to the 4. So alpha to the 4, I talked about this at the beginning of last class. This was just part of the solution to the wave function. So there was this, Now I need an alpha squared here, so let me write this here. Not that that's that hard. MKF, the half. Okay, I need that right here. Okay, so now what? Okay, blah, 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 blah. All right, so I've got h bar squared over 2m alpha squared. Alpha squared is h bar, and then I've got m. Got this on top. All right, then I've got the normalization constant times e to the minus x squared, but I recognize this as my wave function. Okay, so obviously that's my eigenvalue. Assuming that I am about to wipe out this next thing, so I've got my minus h bar squared over 2m. Seriously, that's, is that right? And then I've got h bar squared. Now I'm doing alpha to the fourth, so I've got h bar squared. Just like a puzzle. I'm kind of nervous because I notice I'm not, oh look at that, the m's are canceled, kf. Look at that, it's minus half kf. You see that? It's minus half kf. Oh, but I better have the wave function. The wave function better come back. Sorry, I'm writing this really, really small. X squared. Look what I did, look what I did, bad. I forgot the x squared. God, this is, yeah, I know this is not, this is sucking. I need to, sometimes maybe I need the PowerPoint, because I know this is a lot to look at. But anyway, so it's not hard to see that these cancel. I am left with minus 1/2 kf squared plus 1/2 kx squared, wave function. So these are wiped out, and I'm left with e psi, well it better be e psi, and that is, so again, this might be the hard problem. H bar over 2 and k spring constant over m to the half. If you're confused about the m's, this is m to the half over m, so that is looking m on bottom times the wave function. 2 alpha squared. Okay, sucky, but doable. Question?
Question.
Mm-hmm.
So unless we had already previously solved for alpha squared or alpha to the fourth.
We had, this actually came out of the solution that I didn't do. It's at the beginning of the last lecture. Yeah, it's at the very beginning of the last lecture. When I drew the Hamiltonian, I said, here's the answer. I said the answer is n e to the minus x squared over 2 alpha squared. And I mentioned that alpha was yada, yada, yada. I know it's a big problem when you do a derivation over the course of 2 days. I mentioned alpha was h bar squared over mkf to the 1/4. Yeah, the 1/4, right. Yeah, so that was there. You know, that's one thing, if you're a little cross-eyed, there's like, 10 things you got to remember, and it's spread out over 2 days. And sorry, there's not much I can do about that. It just is what it is. Let me just toss this up here because there's one last thing to do with this, which is to do some, you know, the one thing that's kind of funny is that sometimes classical mechanics, that means Newton stuff, sometimes it shows up, sometimes it doesn't. Like, we actually see some simple things about springs. The energy of the spring is actually showing up here. And other times Newtonian this or that doesn't work at all, like when we talk about how like mass times acceleration would be the double derivative of a function in time. but here it's the double derivative of a function in space, which actually really makes no sense, but that's what it is. Anyway, okay, so what we get from this is that the energy, I'm just going to write it again, is h bar over 2, okay, F over m to the half. Now, what I was blabbering about before was that, oddly enough, this is frequency. So the spring constant over the mass to the half, that's the frequency of the spring. You know that frequencies have resonant frequencies, right? So a lot of equipment, a lot of MEMS devices in Apples and whatnot are built with spring. You know, some springs don't look like springs. Like you can take a metal. Have you seen this before? Take a metal strip and wind it to a circle. That's actually a spring. And so they all have a resonant frequency, and then those are used to make things happen, which I kind of above my head. So this ends up being h bar frequency over 2. Okay. It's a lot of work to just whittle it down to that very simple result. I notice that, of course, we're talking about the ground state. Now, you know how mathematicians like to do things. Here's how I would do the following. So what about excited states? What you could do is do the same jazz for the excited states. I actually did that once on homework, but I felt really bad about it because what you end up with is, remember that the excited state has an x in it. So you actually run into a product rule on the first step, which is just awful. So I didn't ask that again, just do the ground state. But what I would do to ask for energies of the excited states is I would just do a bunch of them and try to find a trend, hoping that there is one. Well, there is. It turns out that the energy of any particular state, maybe you've seen this before, I think you probably should have seen this in some of your forays in you know, some of the simple descriptions you had of quantum mechanics and even in freshman chemistry. Ends up being the quantum number plus a half times that. Now, I know that mathematicians, so, you know, like I say, the way I would do this is I would plug in like 5 excited states, maybe I could get the computer to solve it, and you probably would notice this trend really quick. And, sure, and then you just assume that it's just quantum number plus a half, and you'd be right, but I know that mathematicians never do it that way, so I think that they do some fancy math tricks to solve that this is always the energy. So, and it is, and there you go. Some things to note about that, which is kind of interesting, is actually there's 2 things, and then I was going to tell you that there's something really kind of interesting about is that I'll show here in a second. Okay, so what about the energy? You've heard, of course, you've heard ground state energy, right? Zero, what am I saying? Of course, ground state energy. 0 point energy. You've heard the concept of 0 point energy, which is that things are always moving. I like to pick on CH bonds. CH bonds are always vibrating in their ground state. And so the way you represent that is, like in this potential energy surface, at the bottom is 0, so I've drawn it a little displaced. The bottom is 0, but the first rung is slightly above 0, and that's that half doing that. The other thing to note is that unlike, this is where it's a little different than the particle in the box. The particle in the box, the rungs go up as the quantum number squared, but here it's linear. So it's, seriously, it's just like a ladder. There you go. I just feel like labeling it. And I'm done. You can all go. No, I'm just kidding. So, let's see. There's one other thing I want to mention about that, and maybe don't write this down. I don't want to confuse you. There's just one thing that I think is kind of interesting about this is, remember I said that this is a CH bond? Is it? Or is this a particle? Is this a particle? Draw a little circle. Is it a particle in a little sphere? Which is it? Now remember that when I started solving this, look at that, I used mass. What's the mass of a CH bond?
2 electrons.
What? What? Two what? 2 electrons? No. What? Well, all right, versus an HH bond. What's the mass of that? No, I see what you're, sorry, I see what you're thinking. You're thinking of the electrons that form the bond, which is actually, I actually appreciate that. That's good thinking. But now you would know that a CH bond, your intuition. Okay, now here's how you get out of that logical idea. So they were thinking of what forms the bond, and that you always think of bonds forming two electrons. I like that answer. All right, the problem would be that then all bonds have the same frequency because all bonds have two electrons. What?
Not all elements share their electrons equally. Though.
No. You guys are way off. All right. So here's what's happening. We'll do CH. Remember that these are the atoms moving. Yeah? These are the atoms moving. The electrons actually are hardly perturbed with this. I never actually introduced electrons in this model. This represents the motion of the atoms. And the electrons, it's like the surface of the atoms are the electrons. Now notice that if you think of this purely in terms of the electrons, then these would be identical, which they're absolutely not. Now hopefully you've had enough analytical and whatnot to know that this is a very high frequency. This is kind of medium frequency. Let me give you like what is like the lowest frequency. Iodine, and give it a negative charge. That's like the lowest frequency thing people can humanly make. I think there's one thing that has a lower frequency than that, but that's about it. And again, they're like moving with respect to each other. So the mass is not really got nothing to do with the electrons, but the weight of the atoms. Okay, now again, I want to point out, my question to you is, what did I really solve? Did I solve the wave function of a particle in a parabolic well, or did I solve for the vibrational motion of two atoms that are bonded? Which one is it? Both. Yeah, I said both. I did both simultaneously. So that's the crazy thing about quantum, is that the models can be used to describe completely disparate things, but actually they're the same. It's a real kick in the ass. But anyway, the way that works is, if you're going to think of this as a little ball trapped in a little, it's like a skateboarder, right? Then that's the mass of the particle. When it comes to these guys, the mass becomes reduced mass. Remember when we did reduced mass when we were doing relative velocity? Right, so the thing that should have gotten you is every one of these is different, but notice like a CH bond versus like a CC bond, there has to be a difference. It's the mass. Mass of what? Which one? Both of them? Both plus a half? Well, that's closer. It's reduced mass, right? So reduced mass, of course, I think in case you forgot, which I kind of forgot, that's why I'm looking it up right now, is M1, M2 over M1 plus M2. Okay, so I was always kind of fascinated by this. If I plug in a mass, I'm describing a billiard ball at the bottom of a hill. If I plug in a reduced mass, all of a sudden it's a CH bond, or bond whatever the reduced mass is. Okay, now the reason that's important, I just think that's cool, but anyway, the reason that's important, I'm going to do an application, and then I'm going to show you something that's really, really, really weird that it's a physical chemist to me. I'm kind of surprised they haven't kicked me out yet for a bunch of reasons, but I was hired as a physical chemist. I warned them that I wasn't. They chose not to listen to me. That's their choice. I'm really a synthetic chemist. I'm a semiconductor synthetic chemist. But I used to be a physical chemist, so they mislabeled me. So I'm going to show you an interesting problem that I ran into when I was a real physical chemist. Okay. Anyway, so in terms of application, this is a diagram I want to show you. Okay, let's draw a small parabolic well. And again, I told you that I kind of like CH bonds. So here's a CH bond. But if you have, let's say that you had a deuterated, if you had a deuterated bond, what you would have is a different frequency because the mass is heavier. So it turns out that the reduced mass, when you've got a hydrogen, it's when you go to deuterium, it changes a lot. So, okay, so when you solve for the angular frequency, the force constant over the reduced mass, what you find is that a CD bond, the angular frequency is less by 1 over the square root of 2. Obviously, the square root of the difference in mass between deuterium and hydrogen. So if I draw the 0-point energy, I would do it like this. So let me put a little dash in there so that you know that I'm putting two different things into the same potential well. Now, one reason this works, by the way, is that the angular frequency. So again, you can see the square root scaling because the angular frequency is square root of mass. Sorry, I need to be using reduced mass. Sorry about that. But notice that this is really kind of interesting is that a deuteron still has 1 electron and 1 proton. Hydrogen atom just has that. Hydrogen has 1 proton, 1 electron, but a deuteron has 1 proton and 1 neutron. Now the neutron really doesn't change it to the outside world. It makes it heavier, but the way it interacts with things is identical. So it's really kind of nutty. It's like my 2 cats, right? Charlie and Zoe both have cat legs, and they both have the same power plant inside of them. So they interact with the world the same way. However, Charlie is about half Zoe's weight, so she goes twice as fast. She still does cat things, but she does it twice as fast as Zoe, but it's still a cat. So a deuteron and a proton, if we were to shrink ourselves down, and we were to hold it, we would not perceive any difference. We would not be able to tell the difference until you shook them. Like when I get Charlie, I'm like, you damn bad cat. And so, I don't do that. All right, so now the reason that this matters is, notice that I've done, and this is, I'm kind of going down the well here in terms of nuances, but bonds are not really parabolic, right? They actually look more like this. When you get closer to two things smashing into each other, the potential rises very quickly, but if you pull things apart, eventually they'll snap and then they're okay. They don't really care anymore. In fact, this isn't uncommon either. This kind of behavior is not uncommon. So notice that if you have a CH bond is rather easy to get over a hill, and you would do that by heating the chemical very, 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 very hot, or shining very intense infrared light on it as well. That would also work. A CD bond takes a measurably larger amount of energy to get over the same hill. And this ends up being a mechanistic thing. Now, you've heard this in organic, right? So when you're looking at how, it's fine to just throw things in a pot and see what comes out. And so a lot of synthetic chemists do that. And either they focus on making really complicated things, and so that's like group A. Group B focus on mechanisms. And by mechanisms, if they have some product forming and they think that a CH bond is broken in the process of that, that's actually rare, by the way. CH bonds are really hard to break. What they do is they throw in a deuterated version of whatever, and they look for a different rate. And of course, if the rate, I guess the rate is slowed down in this case, if that's the case, then you would know that a CH bond is broken in the process. So that's, anyway, that's a big part of what these guys do. Okay, last bit, and I guess we won't get to rotation. Let me show you something else, and this actually applies to this, and this I think is really kind of neat. Okay, what we call, what do I want to be here? If E is equal to V at turning point, Okay, I am using a lot of language at once, I'm using a lot of shorthand. Okay, a turning point is, we think of, now remember that the center of the vibrational well is centered at the equilibrium point. We think of the, okay, they compress, they stretch, they compress, they stretch. What do you think would define when they've stretched as far as they're going to go? What do you think defines when they've stretched as far as they're going to go? Right, E is equal to V, right. Because that's all its energy. If it has no more kinetic energy, which would happen when all the energy is potential energy, how can it move further, right? You know, all the energy is potential, well, there's no kinetic energy, so it's going to snap back, right? That makes sense. Okay, now let's do the ground state. Remember, if the energy is, we just did this, but we set that equal to the potential energy, and we'll call that the turning point. Then we do some calculus to simply show this. Not exactly hard. Okay, now I told you, this is like one of the weirdest things, like in the history of things ever. Okay, now let's take the wave function, which is a probability density. Let's do this. Okay. Now, we know how to interpret that. That's the probability that you're going to find something somewhere. And let's ask what the probability is that you are at the turning point or further. Now, what this means is, we think of a bond as doing this, and let's not worry about compression. It's easier to think about expansion. When it's here, when all the energy is potential, it should stop. And that should make this what? Now, this is the probability it's past the turning point. This is the probability it has a, let me give you another more dramatic description. This is the probability it has a negative energy. Should be 0, right? Right? Well, now, you know that these wave functions look like this. All right, you know that a Gaussian, does a Gaussian ever, e to the minus x squared, does it ever actually reach 0? For what 0 is e to the minus x squared 0? And I mean exactly 0. Infinity, right. It doesn't exist. So that's another way of saying it doesn't exist. Okay, so what you do is, okay, this ends up being a real pain. What you need to do is solve this. I may have you do this on a homework at some point. Actually, I think I've decided not to, but what you need to do is to note that that this is equal to 1. To do this on an online integrator, and therefore the integral from minus infinity to the turning point. I do have you do a version of this with the hydrogen atom, by the way. So you actually see this behavior in a whole bunch of stuff. Okay, so what I've done is I've set, sorry, what have I done? I'm being an idiot. Okay, so the integral from all over is 1, that's normalization. What I've done is broke this up, because when you do this online, this one's solvable, but I've never found one online. And of course, I mean, I do these online because Jesus. So that one, that's the one you're looking for. So you just take 1 minus the one that the Wolfram or Symbol Lab deal will solve. I swear, I mean, professionally, I use those all the time because I'm just, yeah, I mean, I'm not going to wait. I'm not even sure how to solve these in all honesty. I should have did that. Okay, what you end up with is one, just so you know, for you to practice. Again, I decided not to assign this at the last moment, and the turning point is defined up there. The normalization constants squared is this. I mentioned I would throw a normalization constant. This is for the ground state, e to the minus x squared over 2 alpha squared. And what this ends up being is in case you want to actually try this. For alpha, square root of pi, just for the hell of it. Alpha square root of pi, over 2 plus n, just to get you used to what. Now you see I know that when I was solving this before class, you got an earth. So that's one reason I like to bring this up is because there's an earth. And again, if you feel like solving this, ends up being 0.0786, which is roughly 8%. 8%. Okay, so the crazy thing is that these things stretch further than they can stretch. And that's true. I mean, I don't know how else to express that. I told you, quantum does really nutty things. Things stretch further than they can stretch. It's basically like tunneling. So let me show you what a consequence of that is, and let me just borrow this graph because I know we're out of time. Imagine you have a potential surface like this. I'm kind of working this backward. What happens is you've got yourself a wave function like this that has some finite probability of being outside of some barrier. So what happens is molecules sometimes just fall apart. If you synthesize something, but you synthesize something with a potential energy surface like this, every now and then, it might be slow, it may take days, every now and then the bond just simply falls apart, even in the ground state, because it just tunnels through the barrier, and that's basically what you're seeing here. This wave function has some probability of being past this point, and if it happens to go far enough, the whole damn thing may fall apart. We occasionally see this behavior in very poorly put together molecules, and when they fall apart, this is why they do it. So anyway, just kind of a neat thing that sometimes happens.